Section 3.5, counting methods. So the goals, be able to use the multiplication principle, be able to compute permutations, and be able to compute combinations. So why counting methods? Why do we care about these things? Well, if you remember, one key element of being able to compute probabilities is to know the number of ways an outcome can occur and the total number of outcomes possible. So you have to know a number for these things. And this can be tedious to do if you try to list them all on paper. For example, there are over 2.5 million 5-card poker hands. So when we were doing things with the tree diagram, it might have got up to, I think the biggest one we saw is it got up to 12. And even if you did 2 rolls of a die, there's 6 on the first, 6 on the second, 6 times 6, you'd have 36 branches at the very end. That's still kind of getting up there, but try thinking about how to do 2.5 million 5-card poker hands in a tree diagram. It's going to take you forever. And mathematicians quickly, I think, moved in the direction of looking for better ways to count the number of outcomes and the total number of outcomes just by using some formulaic approaches. And that's what this section is going to be about, is, counting outcomes without having to list them all out first. That's really at the heart of this section, time saving. So the multiplication principle. Multiplication principle has been used before in this class to help find sample spaces. We were looking at how many were going to be in the sample space. And, we were able to do for that one example with coins, 2 times 2 gave me 4. And that told me, all right, yeah, there's 4 items in the sample space. So we're just going to formalize it now. And recall that we can use a tree diagram to help visualize things. So to kind of build this up here, we're going to consider a pizza place with 2 sauces, 2 cheeses, and 6 toppings. Maybe not the best place, but hey, maybe they're small. So if customers get to pick 1 sauce, 1 cheese, and 1 topping, how many different pizzas can be made? So if we do a tree diagram here, and you're going to have to be very careful when you draw this, make sure that you leave enough space. So I'm going to have the sauce, and I'm going to really open this first branch up pretty wide because there's going to be a lot of stuff coming off of these. And then we'll have the cheese after that. And there's going to be 2 cheeses, so 2 branches off of here. And again, this one I'm going to open up pretty wide. And then this one open up relatively wide. And then we'll have our toppings. And there's 6 toppings. So there's going to be 6 little branches coming off of this. There'll be 6 branches coming off of this. 6 branches off of this choice. And then last but not least, 6 branches off of this choice. And it's not so important that we know, what types of sauce, the types of cheese, what types of toppings. What I want to focus on in this example are the number of end results down here as we follow each of those paths from the root down to the end of each of these branches. And if you look across here, what you're going to see is that there are 24 total ends, or 24 total possibilities. If you're thinking about the number of pizzas that could be made in this way with 1 of each, then you would be able to do 24 total pizzas. So how can we get that number 24 without drawing this entire tree diagram? Well, you notice that there are 2 options for the sauce, 2 options for the cheese, 6 options for the toppings. And if you note that 2 times 2 times 6 equals 24, that's the quick way right there. both these numbers match. And it's much quicker to do this as just, there's 2 for the sauce, 2 for the cheese, 6 for the toppings, 24 ways to pick one of each type, or one of each category. So basically what the multiplication principle says is if there are n ways, and this 2 shouldn't be there, of choosing the first item, and then n2 ways of choosing the second item after the first item is chosen, n3 choosing the third after the first 2 have been chosen, and so on until there are n sub k ways of choosing the last item after the earlier choices, then the total number of choices overall is just given by the n1 times the n2 times the n3 all the way up to nk. So just like we saw up above, this 2 times 2 times 6, there would be n1 ways or 2 ways for the sauce, n2 for the cheese, and n3, 3 would be k here because there's only 3 things going on, but there would be 6 of those ways to choose the toppings. And we saw the n1 times n2 times n3 gave us a 24 total number of choices if we're picking one of each. If you start choosing more than one of each, it gets a little bit more complicated. But multiplication principle is designed for like one of each thing, basically. So another example here, taco stand has 2 shells, flour and corn, 4 types of filling, pork, chicken, beef, and veggie, 3 types of cheese, Oaxaca, cotija, and queso fresco, and 3 types of toppings, sour cream, avocado, and pico de gallo. So the stand is running a special where a customer can build a $1 taco with 1 shell, 1 filling, 1 cheese, and 1 topping. How much would a customer have to spend to try every different type of taco that can be made in this way? Another way to think about this would be like, how many different types of tacos can be made in this way? And if it's, $1 each, then basically the number of ways is the same as the amount you'd spend. Well, you simply just have to take that there are 2 shells, 4 types of filling, 3 types of cheese, 3 types of toppings, and do 2 times 4 times 3 times 3. And when you figure that out, you get 72. So 72 types of tacos at $1 each, the customer would have to spend $72. I'm feeling like I want some tacos. But anyway. So another one like this that uses multiplication principle, and this is a classic type when you start looking at license plates, code words, things of that nature. These are classic problems that they like to, throw at the introductory level student. So license plate has 1 letter followed by 3 digits followed by 3 letters. How many different license plates can be made? So when they give you something like this, where it's like letters, then digits, then letters, what I like to do, and I find is very helpful, is I like to write blanks. So there's, 1 letter, then there's going to be digits, digit, digit, and then there'll be 3 more letters. And just, if you do this, it helps kind of organize things a little bit. And whatever numbers I put up top, I'm going to end up multiplying across because of that multiplication principle. But it's a lot easier to kind of get a framework for where things are going to go. So then you have to remember here, there's 26 letters in the English alphabet. 26 letters total. Not everybody seems to know that off the top of their head when I ask that in class. So just want to clear that up. There's 26 letters A through Z. And then there are actually 10 single digits. The 0 is counted. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If you count them out on your fingers, you'll see there's 10 digits, 0 through 9. And then A to Z. So then up here, we just need to think about, all right, so for that first letter, there's no restrictions on it. It could be any letter. So there will be 26 possible letters that can be chosen on that first character for the license plate. Then you move to the digits. And it's like, well, there's 10 digits that can be used here, then 10 digits that can be used here, 10 digits that can be used here, and then 26 letters, 26 letters, 26 letters. And when you work this out and do the multiplication all the way across, you get a pretty big number, 456,976,000. A lot of license plates that can be made in that way. All right, so that's basically the multiplication principle. You just see how many of each type there is as you're building things up, and you multiply them all together. That's why they call it the multiplication principle, because you're going to be multiplying things at some point. So let's move into permutations. And permutations can help us count the number of ways to select a few distinct items from a group. And when they say distinct items, it means that you can tell the difference between them. So again, it gets a little bit more complicated if you have items where you can't tell the difference. Like for example, if you're dealing with a bag full of balls, and you have like 5 red balls, well, they're all going to look the same. And that's not what the permutation concept is designed for. It's designed for things where maybe each of those red balls has a different number on it or a different letter on it, something that would make each of them distinct from the others. You can tell the difference between all of the items. So when they say distinct, you can tell the difference between them just by looking at them. And what we're going to do here is select a few distinct items from a group when order is important. So things like choosing a president, vice president, secretary, treasurer, where there's named positions, the order in which those people are placed in those positions would be important, because one person is going to be a president in a much different way than somebody else is going to be president. And if you're arranging books on a shelf, there's a certain order that goes along with that. You have the first book, second book, third book, and maybe you're doing them by color, maybe you're doing them by author, or, your favorite genre or whatever. The order becomes important there. There's other places where order is important, but those are kind of some classic ones. If you're putting people in order for a photo, the order in which people can stand for that photo or sit in chairs if they're, you're taking a bunch of pictures of people sitting down. The order in which they line up is going to matter. It's going to make things different. So another classic example here, if 54 people are in a race, you can find the number of possible first, second, and third place outcomes by doing the following. You just kind of do that blank setup like I did before, and you say here, okay, there's first place, second place, and third place. And if there's 54 people in the race, starting at the race, the beginning of the race, there's 54 people that could theoretically come in first. And then after that first place person crosses the finish line, there's only 53 people left that could get second. And then after that person, after second place is done, first place is done, you got 52 people left that can do third. So altogether, this would then give you 148,824 different outcomes for first, second, and third place in this race. So we'll take a look at the better way to do this in part 2.